Good morning, again, recording. Sorry, I forgot to change the due date for those assignments like I said I would, but if that happens again, I can't remember who it was, but someone just texted me and was like, hey, you actually said you were gonna change it. Yeah. Mea culpa, sorry guys. And if it didn't change in time or whatever, I gave you guys till Saturday. I'll have a look, and if you need me to open it up again, I can, but it should be pretty good. So, all right. So that was my bad. I apologize. But thank you for just letting me know. And probably text is best. Because I think it was in the evening, so in the evenings I don't really check my email that much. So definitely, if you need to get a hold of me, just text me, like that. Stuff like that. If I've forgotten to do something, like I came down this morning and I was like, there's something I was gonna do, but I'm feeling pretty good. So so I couldn't remember, and then I was gonna do the solution. So I've got it here on my little to-do list. So after, well, I've got a class right after you guys, and then after that, I'll get those solutions up and posted for you guys. So just use these the problems that are in the notes as practice, and then I'll get you those solutions, and we'll be good to go. All right. So I'll also post a couple from 1.1 and 1.2, those fundamentals part 1, but there won't be a ton of problems from there. So yeah, but there's also, like, it's a lot of material, but we'll see. All right, so this week we will finish fundamentals part 4. So we're going to talk about inequalities, and we're going to talk about lines and graphing, lines, and finally graphing. Okay. In the notes, this is inequalities, section 1.8. No worries for being late. You do not need to show up even, so showing up, that's a good thing. Look at this full classroom. Let me just count. We're at 14, I'm 2 of those, 12. But I think we're only missing 3 people. It's not bad. Because I'm pretty sure there's only 15, or is it 13? Anyways. Oh yeah, so in the fundamentals part 4, inequalities is called section 1.8. Remember, I've stolen this from a different textbook. So the numbering isn't the same as our free textbook, but hopefully you guys are okay with that, because you're getting a way more solid fundamentals than in the free textbook. So we're just kind of grabbing from where we can. The lines is called section 1.10, and then the graphing is called section 1.11 in fundamentals part 4. So we're kind of skipping around, well, not skipping around, but we're skipping through a couple of sections because we don't actually need them. Once we're done this week, right? The graphing one we'll just kind of touch on. We're not gonna get into it so much until later. But once we've talked about inequalities and lines, then we're going to have a really solid foundation for moving forward. So that feels really good. And then we'll have our test next week, right? So test number 1 we meet Tuesday, Thursdays, right? On Thursday next week. Remember that Monday is a holiday. We don't have class on Monday. So Monday, no school. But on Tuesday, we'll do a test number 1, review day. I'll give you guys more information about how I want to do the test. Once I figure out how exactly I want you to do the test, I can't decide if I want to just upload a PDF and then you guys work through that and give me your work, or I can't decide how I want to do it. So how are you guys doing other tests? I can always talk to Allison too and see what you guys are used to doing, because it might be easier if I just stick to that. But yeah, so if I post a PDF, yeah, I was gonna use my open math, but because it can be a little bit tricky, I think I'll just do kind of written work, but like I said, I'm still deciding, so we'll see. Not open math. Multiple choice is so hard. Yeah, multiple choice, that's too hard to do, not to make. To make, it's easy. But maybe some multiple choice. Yeah, so we'll see. I don't know if you guys have access to a printer, or, well, because you guys have a different situation, right? I think you're going to classes for labs and stuff. So you guys are at the school sometimes. Anyways, I think I'll talk to Allison and see what the easiest thing to do is. All right. Oh, no printing, huh? Weird. Okay. Huh. Things change, right? All right. No test is sort of an option, not really. Hey, that sounds great to me. I don't have to mark it. Yeah, sounds nice. We'll just keep flowing through the course. It's win-win. Exactly. I love it. I love it. I love it. Okay. So, yeah, I'm gonna try to do 3 midterms because it's gonna be nice to break it up kind of and have a couple of check-in points. So we'll do this, like, I've called it fundamentals, but I was talking to a colleague and he was like, yeah, these courses, because the pre-calculus, and this is basically a pre-calculus course, and I'm like, it's just taking me forever to get through the fundamentals. And he was like, well, yeah, it's like 30% of the course, so yeah, it's gonna take a while. So don't worry, we are on track. But yeah, so I am gonna do 3 midterms still, and then the final, yeah. So, oh yeah, so we're gonna have 3 midterms. We will have 3 tests. Can't call them midterms. Technically, a midterm has to be 1 test in the middle of the term. Anyways, terminology, right? And a final exam, and a final exam in the final exam period. So it'll be scheduled by the college, and we'll just write that final exam whenever they tell us to, and it'll be in the final exam period. And the final exam is 3 hours. It's not worth very much. I think it's worth, what did we say, 20, 25% now because we're online. But yeah, it'll be a little bit longer. It will be cumulative, whereas the tests, I try to keep them as focused as possible. So all the new stuff gets tested. And then what's nice about having 3 tests is that we can have a test way towards the very end so that you'll have seen all the material on a test at some point. Okay, so good. So what we'll do, especially for the review day, I'll have posted a practice final practice final, I'm already in final exam time, no, a practice test by then, but also I'll have outlined how I want to do the submissions, etc. So in the review, we'll go through a couple of the problems, not all of the problems. So definitely bring, your questions from the practice test that you want to go through. But also, I'll just really walk you through how I want you to do the test, right? Whether that involves, writing out your questions or scanning or whatever. We'll talk about that on the review day. Okay, so that's after Thanksgiving, which is coming up this week. All right. Any other questions, comments before we get into some material here? Okay. Thanksgiving, I know. It's nice if you have classes on the... Wait, are you actually going to Edmonton? Coming to visit me? You're driving, yikes. It's a long ass drive. I guess it's not that bad. We just, before school started, we had to go, oh nice. We had to go from Edmonton to pick up the dog in Vancouver, and we did the Edmonton-Vancouver drive in one day. And we're never doing that again. I'll always fly from, yeah, it's a lot. And then we went to Kelowna, and then we went to, stayed the night in Vernon, and then, so that's, yikes. Yeah, it's a long drive. Anyways, drive safe. So far, I've only done it once. All right. Usually we do a little summary of what we did last week, but honestly, I'm drawing a blank. I can't remember what we did last week. So, okay. Dealt with some algebraic expressions here, multiplying, dividing, dealing with those fractions, common denominators. Some more factoring. Man, we did a lot. Okay. Compound fractions, all right. Difference quotients, although we probably didn't call them that. Oh yeah, rationalizing the denominator, rationalizing the numerator. Okay. Kind of a review. We dealt with algebraic expressions, multiplying and dividing. We talked about, oh, now I can't remember. Multiplying and dividing, compound fractions, which are just kind of fractions in fractions, not necessarily all fractions. And then we talked about rationalizing the denominator or numerator, whichever. Usually we rationalize the denominator, but sometimes we have to rationalize the numerator, and then that's when we have to multiply by the conjugate. Right, so there. Sort of a review, not really. Today, I'll start it on a fresh page here. We're gonna do 1.8, sort of, inequalities. So we're gonna talk about inequalities. So up until now, I've been saying, you know, if you have an inequality, just treat it as an equal sign, and we'll talk about the specifics later, right? Because there are instances where we can't treat an inequality as an equal sign, and that's what we're gonna talk about today. So up until now, we have treated inequalities, which are the less than or equal to, greater than, equal to, right? As equal signs. I guess I'll just do a period there. That's a fact. But today, we'll highlight the few scenarios where we cannot do that anymore. Okay? So we will now highlight the few scenarios where we can't do that anymore. Okay. Number one is if you end up multiplying or dividing both sides by a negative number, right? So division is essentially multiplication. So the first scenario, kind of the most common scenario, there are two, but I would say the multiplying or dividing by a negative, that's the most common thing that we need to look out for and really be aware of. Okay, so if we multiplying, oops, or dividing by a negative number on both sides of an inequality, switches, and I'll put switches kind of in quotes, switches the sign. Okay. So just as a quick example, we can say that 1 is less than 4, right? But if I multiply both sides by -2, right? 1 times -2 and 4 times -2, right? What happens here is I have to switch the sign because I'm multiplying by a negative number. So this actually becomes negative, so 1 times -2 is -2, right? Has to be greater than 4 times -2, which is -8. -2 is greater than -8, right? And so what you get is -2 is greater than -8. But that's only true because we switched the sign here, right? When we multiplied by a negative. This one is so, so important. Okay. So in general, yeah, we can treat these inequalities as if they're equal signs until we're multiplying or dividing by a negative number. Then we have to switch the sign. But as long as you just kind of revolving door that sign, then you'll be safe, right? And you can do a little check-in point like this just to convince yourself. Okay. The other one, which is less common, I'll put that because if you're going to focus on rules, definitely focus on this first one. And then this one, of course, keep it in mind when you're working on problems. But in general, it's not going to come up that much. So just be aware of it. If taking the reciprocal, so 2 becomes 1 over 2, right? So 1/2. If taking the reciprocal of both sides of an inequality, we need to switch the sign. So as an example, right, 2 is less than 4, but taking the reciprocal of both sides, right, 1 over 2 is greater than 1 over 4, right? 1/2 is greater than 1/4. So if we take the reciprocal, then we have to switch that sign. And these are the two situations where we have to be really careful and just remember to switch the sign. Otherwise, your answer is going to be wrong, right? So just be really careful. So if you go to the notes that I posted, right, so inequalities, this is fundamentals. Part 4, we've got these kind of fancy written out rules. What we just talked about is rule 4 and rule 5. So let's just see here. Oops. So here we've got all rules for inequalities. Rule number 4 and 5 are above. Okay, so those are the ones that we just talked about. So if you add a value to both sides of an inequality, the inequality stays the same. If you subtract a value from both sides, then the inequality stays the same. If you multiply by a positive number, the inequality stays the same. So everything stays the same. And then here are the two situations where things change if you've got an inequality. And then inequalities, you can add inequalities. So if you know that A is less than or equal to B and C is less than or equal to D, then A plus C, so kind of adding both left-hand sides and both right-hand sides, the inequality would stay intact. And then if A is less than or equal to B and B is less than or equal to C, as you say it, right, we know that A must be less than or equal to C, which is just another way of saying that it's transitive, right? So it kind of goes, the alligator keeps eating, I guess. Right, so inequalities kind of work through and cascade through that way, which makes sense. Okay, so what we're going to be working on is we're going to be working on solving linear inequalities, and then we're going to talk about solving nonlinear inequalities, but we're going to focus on quadratics. So focus on polynomials with just an x squared. Okay. So here is just a little note of what we just talked about, where we're multiplying by negative, right? It's the most common thing that we're going to do, so so we need to keep track of it. Okay. So if we're solving these things, right, solve the linear inequality just means solve for x. Right, whenever you have to solve something, it's usually solving for x. And then we're going to express the solution in interval notation, and we might graph it just to have a look. Okay. So if we have to solve for x here, which ones should we, let's start, we'll start nice and kind of, this one's the first one where we do any real rearranging. Okay. So how about, let's do 16 first, and then we'll do 20. So 16 says 3x plus 11 is less than 5. So now, remember, you can treat this inequality as an equal sign as long as you've got a little check-in point. If I'm multiplying or dividing by a negative number, then I need to switch the sign, but everything, I can still do that, right? Or if I have to take the reciprocal, which we'll just kind of keep on the back burner. So if I'm solving this thing for x, right, first thing I have to do is I want to try to get x on its own. So I have to get rid of this 11, so plus 11, which means I have to subtract 11 from both sides. So then I have 3x is less than 5 minus 11. Notice that I'm not showing the minus 11 on both sides. I am cheating a little bit. It's not cheating. I don't expect you to show the minus 11. If you want to, that's fine, but I'll just show it on the one side and how I'm slowly moving through all these things here. So 5 minus 11, too early for me, is negative 6. So we've got 3x is less than negative 6. Okay? Now, just as a little stopping point here, to get x on its own, I'm going to have to divide both sides by 3, right? Because I'm multiplying 3x, or 3 by x. So to get x on its own, I have to divide this by 3, which means I have to divide both sides by 3 in order to move this 3 over to the right-hand side. Because I'm dividing now, I need to have a mental check-in that it's not a negative number. If it's positive, I'm safe, right? So here, I need to do x is less than negative 6 divided by 3, right? The sign stays the same because it's a positive number, right? Which means that x must be less than, oops, negative 2. Okay. I don't know about you guys, I never liked inequalities. I think they're kind of hard to think about. And especially if you're first starting with inequalities, then it's a really good idea to just check in. Oh yeah, why negative 2? Negative 6 divided by 3 is negative 2. So, sorry, I forgot to show it. Negative 6 divided by 3 is negative 2. Cool. So like I said, if you're not feeling that confident with, oh, did I switch the sign? Did I do it right? You can always check your work by plugging in a value here. Okay, so what this is saying is that in 3x plus 11, it has to be less than 5 as long as x is less than -2. So what you can do, you can check your answer right by picking a value, right, by picking x equal to -3, maybe, right? Or what's easy here? Yeah, sure. Right? And x less than -2. Careful on the negatives, right? Because negatives here at 0, if you're at -2, what we're saying is that all these values are solutions. Right? X less than -2, not equal to -2. So just graphically, I guess we ended up doing it graphically anyways, right? So what we do is we pick a value that's in the solution set, or what we found to be in the solutions. And then, so I picked -3 arbitrarily. I just picked a value that's less than -2. And what I'm going to do is I'm going to plug this in and make sure that that's a true statement. Okay? And so what I'm going to do is I'm going to say 3x plus 11 less than 5 must be true if x equals -3, for example, right? Because it's less than -2, so that's what we said. So 3 times -3 plus 11, is it less than 5? So 3 times -3 is -9, plus 11, 2 is less than 5. So we did it right. Okay. So the solution then, solution in interval notation, okay, if we go back, x is less than -2, which means that all values up to -2 from -infinity, so from -infinity up to -2, but not including -2. And graphically, we already did it. Oops. Here, -2. Whee. There's our solution. Okay. So let's do, so that was just a, I'd say, relatively easy one, right? Because there's only one value of x, so we didn't have to collect like terms and then move things around. So let's see 21, where we have 2 values of x floating around that we need to collect before we can solve for x. So we've got 4x minus 7 is less than 8 plus 9x. So we have to collect all our x's on one side, and then we can collect all our non-x's, right? So here's a 4x, here's a 9x. So what I'm going to do is I'm going to pull these to one side, and then the -7 and the 8 I'm going to pull to the other side, right? Keeping in mind that if I'm multiplying or dividing by a negative, I have to switch the sign. But as soon as you're multiplying or dividing around an inequality, right, just have that as a check-in point. So what am I going to do? I'm going to take it nice and slow for now, right? But in general, I would move this -7 over here and 9x over to the 4x side, or I could move this 4x over to the right-hand side and this 8 over to the left-hand side. It really doesn't matter. Okay. For kind of illustrative purposes, I'm going to collect the x's on the left-hand side and just the numbers on the right-hand side. You'll see why. So here, I'll just collect x's on one side and numbers on the other. So I have 4x, get caught, 4x minus 7, I'll keep that minus 7 here, but then I'm solving this real slow for now. I'm going to subtract 9x from both sides. I'm subtracting, so I'm still safe. And all that has to be less than 8. Okay. So now, right, I moved this 9x over here. Next, I'm going to move this minus 7 over to the right-hand side, which means I have to add 7 to both sides. So I get 4x minus 9x is less than 8 plus 7. Okay. So this moved over here. Okay. I can collect like terms, right? 4x minus 9x puts me at negative 5x. Which has to be less than 8 plus 7, which is 15. To solve for x here, I have to divide by negative 5, right? Need to divide by a negative. Right? So we have to be careful. So x, now kind of highlight that I switch that sign, must be greater than 15 divided by negative 5. And then 15 divided by negative 5 is, of course, negative 3. So x must be greater than negative 3. Okay. So in interval notation, we have negative 3, but x has to be greater than negative 3, so up to positive infinity, but not including negative 3, right? So that's why we have the round bracket. And then graphically, we've got a number line here. Oops. We've got 0 here, negative 3 here. I'm going to have an open dot at negative 3 and then everything greater than negative 3. Okay. We're going to check our work. Check your answer. We can pick any value that's in the solutions here. So any value that's greater than negative 3. Sometimes I look back and I try to find convenient values of x, such as x equals 1 is allowed, right? You could even do 0, right? Check your answer using a value of x from the solution. I'll let x be 1 just so I'm not dealing with the zeros. Zeros makes it too easy. But you can quickly see that 4 times 0, that makes -7 on the left-hand side. 8 plus 9 times 0, -7 is less than 8, so it works, right? Let's do one just to make it a little bit more clear why it works, right? And so we've got 4x minus 7 has to be less than 8 plus 9x. Okay. So if we let x be +1 in here, it's part of the solution, so it should work. 4 times 1 minus 7 has to be less than 8 plus 9 times 1. 4 minus 7 is -3. 4 times 1 is just 4. -3 has to be less than 8 plus 9, which is 17, which is true. So it looks like our set of solutions works, right? Let's say just for kind of, for practice, let's say we had forgotten to switch the sign here, right? The only reason we're picking values greater than -3 is because we switched the sign when we divided by that -5. But let's say we forgot to do that. So then our solution would be x is less than -3. So then you'd have to plug in a negative value, a -4, for example. If you plug in x equals -4, you'll find that this inequality is false. So it's not the solution. So that's how you'll use that as a check-in point to say, oh, I must have forgotten to do something, right? And you can go back and you can check your work. Okay. Kick it up a notch. More like kick it up 4 notches. Let's do question 36. So 36 is the last one on the list here. So of course it's among the hardest. Buckle up. Here we go. Right? We're trying to solve for x. We see only one x, so that's nice. But what we're going to have to do when we've got an inequality on both sides, right? It's wedged between these values. We need to make sure that we solve for x, but we have to manipulate all sides of the inequality. So we got 36 coming our way, which is -1/2 is less than or equal to 4 minus 3x divided by 5, which is less than or equal to, +1/4. Okay. So here, we need to solve for x by manipulating all sides of the inequality. By manipulating all sides of the inequality. Okay. So what I want to do is I want to get x on its own, right? Ideally, I want to get x in the middle of these inequalities here, and I want to know what the range of my x is. Okay? So to do that, it's just as if you're covering up one side and solving for x, just like we were doing, right? But you have to do it to both sides of the inequality simultaneously. So what I'm going to do is I'm going to write this out kind of more clear. -1/2 is less than or equal to 4 minus 3x over 5, less than or equal to 1/4. Okay. First thing that has to happen is I have to multiply all sides by +5, right? In order to try to get x on its own, I have to move this 5 over. Okay? What that's going to look like is, now I'll show it just so that you can see that I'm multiplying all sides of the inequality by 5. Okay? And the reason I'm doing that is because this and this is going to cancel. 5 over 5 is 1. Multiplying by 1 just leaves you by with 4 minus 3x. So now I have negative 1 times 5 over 2. So negative 5 over 2 and then 5 over 4. So I can rewrite this as negative 5 over 2. I multiplied every side by positive 5, so I don't need to worry about switching the inequality. So I'm going to keep it less than or equal to 4 minus 3x less than or equal to 5 over 4. Okay. So that looks better already, right? In order to get x on its own here, I would need to subtract 4 from all sides. Right, so not just both sides anymore, we've got 3 sides essentially. So I need to subtract 4, so minus 4, minus 4, minus 4 everywhere, right? 4 minus 4 goes away. Okay, negative 5 over 2 minus 4. Notice that we're dealing with fractions now, right? In fact, I should write this out a little cleaner so that it looks like an actual fraction, minus 4. There. In order to combine this, right, I need to write it over a common denominator, right? Same thing over here. I'm just going to multiply the 4 by 2 over 2. Right? So I get negative 5 over 2 minus 4 times 2 over 2, getting that common denominator, must be less than or equal to negative 3x, must be less than or equal to 5 over 4 minus 4 times 4 over 4. Like I said, there are more elegant ways of getting a common denominator, but this way always works, right? Whatever you need your common denominator to be, just force it, right? So now you have negative 5 over 2 minus 8 over 2 has to be less than or equal to negative 3x, less than or equal to 5 over 4 minus 16 over 4. Now I've got that common denominator of 2 and 4 here. They don't have to be the same because I'm just subtracting on either side here. So now I have negative 5 minus 8, and don't be a hero. I want you to use your calculator because any silly little mistake here is going to cost you, right? And so I want you using your calculator. Negative 13 over 2 is less than or equal to negative 3x, which is less than or equal to 5 minus 16 is negative 11 over 4. Okay. So close. I'm solving for x, right? Which means I have to divide every side by negative 3, a negative number, right? And so dividing by negative 3 is essentially multiplying by 1 over negative 3, right? And so here, what we get is we get negative 13 divided by 2, and then I'll show you multiplied by 1 over negative 3, right? This here is the same as dividing by negative 3. Multiplying by 1 over negative 3 is the same as dividing something by negative 3. And you can use the fraction over fraction to prove it. Which now, right, I'm multiplying or dividing. In this case, I'm dividing, but I'm also multiplying by the reciprocal. So not to be confused with the reciprocal rule. For inequalities, that's not this, okay? here I'm multiplying or dividing by a negative number, and so I need to make sure that I switch my sign here. X. Oh, and I guess I've been showing negative 3x times 1 over negative 3 has to be, and then the same thing on the other side, I have to switch this inequality greater than or equal to negative 11 over 4 times 1 over negative 3. Negative 3, those cancel. So what I'm left with is negative 13 over 2 times negative 3 is negative 6. Has to be greater than or equal to x, which has to be greater than or equal to negative 11 divided by negative 12. 4 times negative 3 is negative 12. Okay, so now we've got negative 13 divided by negative 6. Do it on your calculator, you'll see that the negatives cancel, right? Negative over a negative makes a positive, divided by negative 6. But it doesn't simplify, especially if you've got a handy calculator that simplifies for you, right? Really useful. So when I plug in 13 over 6, it just gives me 13 over 6, so I know it's simplified. And I want you to leave it as a fraction, right? I don't want you to write it as 2.166666667 repeating, or 6 repeating. Okay. So 13 over 6 has to be greater than or equal to x, which has to be greater than or equal to negative 11 over negative 12 is 11 over 12. Okay. Although it might be useful just to kind of check in to figure out what this is as a decimal, the decimal approximation, right? And the decimal approximation, it's easier to think about than just fractions, but I want to see your answers in fractions because those are the exact values. Okay? Whereas the decimal is the approximation. So here, this is our answer, but usually we write it as, you know, the smallest value, and then, so this is our answer. This is our answer. But it will be easier to visualize if we write it as x, right? Smallest value is less than or equal to x, which is less than or equal to the biggest value. Okay, so as long as you kind of keep your wits about you here, right, 11 over 12 is less than or equal to x, which is less than or equal to 13 over 6. And just to make sure, right, you can check your decimal approximations. This is roughly 2.166 repeating, and then 11 over 12 as a decimal is roughly 0.916 repeating. So it makes sense to say that x is somewhere between these two values. You just want to make sure, but I want your answers in the exact form. In terms of interval notation, oops. So the solution in interval notation is going to be, oh, I guess I need square brackets because it's less than or equal to, so I'll use square brackets instead. From 11 over 2 up to 13 over 6. Oops, square bracket. Okay. Square those up a little bit. And graphically, now in the background, I'm going to make use of these decimal approximations, even though I'm going to put the fractions on my number line. But it's really hard for me to know what 11 over 12 is. So just so I know where to put it on the number line, I'll convert it to the decimal, but I'm still going to work with the fractions, right? Exact values, approximate values, we always want our exact values as much as possible. And I know that's that can be kind of hard to shake, right? We want to deal with decimals because we're used to them. So here we've got 0, and then somewhere around here, I've got 11 over 12, and then roughly 2.1. So here, 13 over 6. Inclusive. So I've got a closed dot, and all the values in between, right? And just as an indicator, here I'll have 1, and here I'll have 2. Right? So now I still want to check my work, right? We can check our answer by picking a value somewhere in this range. And that's why I kind of highlighted that 1 would be in this range as well as 2. So these are nice and easy values to use. So if I plug in x equals 1, the inequality should be true, right? So let's just make sure. Check your work by letting x be 1, right? Or something inside the interval, right? You could use 2 if you want to make sure the inequality is true. We had -1/2 has to be less than or equal to 4 minus 3x over 5, which is less than or equal to 1 over 4. If I let x be 1 in here, right, then I have -1/2 has to be less than or equal to 4 minus 3 times 1 over 5, which has to be less than or equal to 1 over 4. Can simplify in here. -1/2 has to be less than or equal to 4 minus 3 is 1 over 5, which has to be less than or equal to 1 over 4. Again, it's going to be pretty useful to use the decimal approximations instead of the fractions. So -1 over 2 is, of course, -1/2. So let's see here. -0.5 is less than or equal to 1 over 5, which is 0.2, which is less than or equal to 1 over 4, which is 0.25. Which is true. Which means that this is true. Nice. So that's a big problem, right, that we just did. That's a huge problem, actually. So do those other ones for practice that are on there. We can also solve nonlinear inequalities. We're going to focus on either things that have been factored out like this, or quadratics, right? Quadratics, we've looked at how can we factor these using the quadratic formula, right? And so we know how to factor these things, because to solve nonlinear inequalities, so where the power of x is greater than 1, then we need to have it factored. And I'll show you why. And there are some guidelines here, but I'm just going to talk you through those instead. But essentially what we do is we need to figure out where this inequality is true, right? And so on a graph, it's easiest to think of, okay, where is it positive and where is it negative, right? Where is it above the x-axis and where are things below the x-axis? Okay. And so as long as we keep in mind that a negative times a negative makes a positive, right? And a negative times a negative times a negative makes a negative, right? Because you get a positive times a negative is a negative, right? And so we need to keep that in mind for when we're solving these nonlinear inequalities. I'll throw this in the notes here. But also, I'll put these in there right away so that we can look at them. A nonlinear inequality is just an inequality where the power of x is greater than 1. An inequality where the power of x is greater than 1. Right? Here we've got x times x, so x squared would be our highest x. Again, x squared, x times x, x squared, x times x, x squared, 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 blah, 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 blah. They're all x squared, which is good. That's what we want, right? That's what I promised we would have to deal with, unless we've got something written out like this, where the highest power would be x to the power of 3. But what you'll see is if it's factored already, it's almost the easiest one to deal with. Okay? So notice that we've got these inequalities, right? We start out where things are compared to 0, right? Less than 0, greater than or equal to 0. Where is it greater than or equal to 0? All these things. Later on, we can force that 0, right? So in order to solve a nonlinear inequality, what we're first going to do is we're going to factor, and then we're going to set the inequality, one side of the inequality, to 0. To solve, so this is what's outlined here in your notes, but I find that it's really wordy, so we'll just talk it out. Wordy, but we'll talk it out. To solve a nonlinear inequality, first thing you're going to do is set one side of the inequality equal to 0, right? So move all the terms, if they're not already, over to one side of the inequality. So move all terms to one side of the inequality, making the other side 0. as you'll see in those first few questions, that's already been done, right? It's already moved over. So we don't have to set it to 0, but then later that's what we'll do. We'll start by manipulating everything to move over to one side, leaving 0 on the other side. Okay. The second thing you're gonna do is you're gonna factor all the terms. So the side with all the stuff on it. So factor the side with all the terms as much as possible. Okay. Once you've factored, right, you'll be able to find the solutions. So then find the roots or the solutions. Oops, find the roots, which we've just called solutions so far. Of the factors. Okay. So you find the roots. Then what you do is you figure out, okay, use the roots as kind of check-in points and figure out what the sign is on either side of those roots. So use the roots to figure out what the sign, right? So either positive or negative of the factored side of the inequality is. So use the roots to figure out what the sign of the factored side of the inequality is to determine if the inequality is true or not. Okay. We use what's called a sign chart. So I'm introducing these and we'll use these later on in the course as well. So we use a sign chart to do this. Okay. And then using what we find in the sign chart, then we'll be able to say what the solutions are. Very wordy, probably doesn't make sense. So let's do an example. Let's start with 37, right? Nice and slow. So let's do 37. X plus 2 times x minus 3 has to be less than 0. So going through our checklist here, move all the terms to one side of the inequality, making the other side 0. So here, all the terms are on one side and 0 on the other side. So that step is done, right? Otherwise, we would have to move towards this step. The next step is to factor the side with all the terms as much as possible. This is already factored, right? X plus 2 times x minus 3. There's no way we can break this down to make it any simpler. So now we need to find the roots. So the roots of the factors are the solutions of the factors. And so here, x equals -2, because -2 plus 2 equals 0. So it's a solution or a root. And x equals +3, because 3 minus 3 equals 0. So these are our roots. Roots are x equals -2 and x equals 3. Right. If we had used the quadratic formula, the quadratic formula gives you the roots, right? And then what we were doing before when we used the quadratic formula to factor a quadratic equation was we used the roots to develop these factors. So now we're just going backwards in a sense. And so now we've got the roots. Okay. So we'll find the roots, done. The only new thing really is that we're going to use these roots to figure out what the sign of this overall thing is, because we want all the solutions where the total of this thing, x plus 2 times x minus 3, it's all less than 0. Okay. So what we have is now we need to use a sign chart to find where x plus 2 times x minus 3 is less than 0. So we use x equals -2 and x equals 3 on a number line, and we're going to check points on either side here. So we've got this number line, I've got x equals -2 and x equals +3. Okay. So what I'm going to do is kind of like before, we pick kind of test values on either side, or on all sides of these roots. So these are test points. Maybe I'll make them stars so they don't look like X's. So I just arbitrarily pick something on the left-hand side of x equals -2, something between -2 and 3, and something that's larger than 3. I try to pick easy values to work with, right? So something x less than -2, let's say, what are we dealing with here? -5. Something between -2 and 3, well, let's pick an easy number like 0. And then something on the, so greater than 3, let's pick x equals 5 again. All right, see how it goes. Okay, so what I do, or what we need to do, is we're trying to figure out where x plus 2 times x minus 3 is less than 0, right? So we're looking for negative values. And so what I'm going to do is I'm just going to divvy up this sign chart and do the work side by side here. So what I'm going to do is I have x plus 2 times x minus 3, and I want to know, oops, not if it's less than or equal to, I want to know if it's less than 0. If I plug in x equals -5, because that's the region that I'm in here, and then we're going to do it for all 3 regions here, I'm going to plug in x equals -5 here and see if it's negative or positive, right? So what I get is I get -5 plus 2 times -5 minus 3. And often we don't even need to solve it. Here it's easy enough, but we don't need to solve this. We just need to say, okay, what do I want to do here? -5 plus 2. I really only need the sign, right? So it's good to start and actually do the math, but soon enough you'll see, okay, -5 plus 2, that's always going to be negative, right? And so here, this is a negative, times -5 minus 3, that's also going to be a negative. A negative times a negative is a positive value, right? So what this is saying is we've got, right, you could do the calculation, right, but what you'll find is that -5 plus 2 is -3 times -5, oops, -5 minus 3 gives you positive 24, right? And so this is equal to 24, but the whole idea is how does it relate to 0? Right here it's a positive, and so on this, in this region, it doesn't matter what value, as long as you're to the left of x equals -2, then this whole thing, x plus 2 times x minus 3, will always be greater than 0, right? That does not satisfy this inequality, right? And so this is not a solution, right? Because it's greater than 0, it's going to be positive in that region. So let's check in and do the same thing, but just a little bit cleaner, a little bit faster maybe, with x equals 0 as our test point. So I'm going to do my x plus 2 times x minus 3. Well, if I plug in 0, I get 0 plus 2 times 0 minus 3, which is essentially, so now I'm just going to start doing, this is a positive number and this is a negative number. So that's a positive times a negative, oops, not -1, but negative, which is a negative number, right? A negative number means that it is less than 0, right? And so this region is a solution. Okay. Now we do the same thing at the check-in point that we picked to the right of x equals 3, so greater than x equals 3, we used x equals 5. So now x plus 2 times x minus 3 is 5 plus 2, that's positive, right? So you can just kind of make a note. And then 5 minus 3 is also positive. Positive times a positive makes a positive value, right? So not a solution. Because we needed this whole thing to be less than 0, right? Which means we need a negative value. Okay. These quadratics, what they look like graphically in general is something, so we've got roots at -2 and +3. So what this is saying is that, okay, at -2 and 3, this thing is 0. To the left of -2, the answer is positive. So what that means is that this comes in like this, and then it switches to a negative result, and then it switches, still negative, and then it keeps going like this, right? Here we have negative results, And here, these are positives. Oops. Right. And this is positive and positive. Right. And we wanted where it was less than 0, oops, less than 0, that's between -2 and +3. And so going back, right, if x is between -2 and +3, the inequality will be less than 0, which is the solution. So in terms of interval notation, if x is between -2 and 3, but because it can't be equal to 0, right, it's not including x equals -2 and x equals 3, because if we let x equal -2, then this would be 0 times x minus 3, which is equal to 0, which is not a solution. And so our solution is between -2 and +3, not including those endpoints. So we've got -2 up to 3. All right. Oh, that was our first one. Right. What we'll see is we'll start, let's do maybe something like 42, which is x squared plus 5x plus 6 has to be greater than 0. So now, in the end, we'll be looking for positive solutions, right? Greater than 0. And so we've moved all the terms are already to one side, right? So then we've got 0 on the other side. It's not factored yet, but we can use the quadratic formula, right? Because it's in the format x squared plus x plus 6. And so plus 5x plus 6, I should say. So here, use the quadratic formula to find the roots. So the quadratic formula says that if we have x, we're solving for x, it's -b plus minus the square root of b squared minus 4ac all over 2a. In this case, right, a is 1, b is 5. Let's make a note here. A is 1, B is 5, and C is positive 6. So we get -5 plus minus the square root of 5 squared minus 4 times 1 times 6 over 2 times 1. Okay. Not that bad. 5 squared minus 4 times 1 times 6 puts me just at the square root of 1. So -5 plus minus the square root of 1 over 2. Square root of 1 is just 1, right? So -5 plus minus 1 divided by 2. So x is going to be -5 plus 1 divided by 2 and -5 minus 1 divided by 2. Okay. So I get -5 plus 1, -4 divided by 2, oops, and -6 divided by 2. So x is going to be -2 and -3, right? -4 divided by 2 is -2, and -6 divided by 2 is -3. So these are my roots, right? So these are my check-in points, and this is where it equals 0. And then because of how a quadratic looks, right, it's always going to be a parabola. Either it's facing up or it's facing down. But the x equals -2 and -3, that's where it crosses the x-axis. So we just need to figure out if it's pointing down or pointing up, right? And then figure out what the solutions are. All right, so we've got our roots. We could rewrite this as a factor. We don't have to because we've got the roots already. But just to show, let's see here, we've got x squared plus 5x plus 6, which using our factors, right, we can rewrite as x plus 2 times x plus 3. And we need this to be greater than 0. Right? At x equals -2 and x equals -3, it equals 0, but we need this whole thing to be greater than 0. So use x equals -2 and x equals -3 to pick test points. Okay, so what we're going to do is we want to figure out where this thing is positive and negative. So we've got -3, remember, is less than -2. So just be careful. Right? On the number line, -3 goes to the left of -2. So now, right, I'm just going to pick test points again. Maybe x is -6 might be nice. Between -3 and -2, there's not a lot to choose from. So maybe I'll choose -2.5. And maybe here I'll just, as a reference point, I'll use 0, right? Any value. So everything will behave the same up to -3, and then between -3 and -2, it's going to behave the same, so it doesn't matter what value you pick. And then same thing here, anything greater than -2 is all going to behave the same. So what I'm going to do is I'm going to write out, I've got x plus 2 times x plus 3. Instead of actually solving this thing, I'm just going to imagine plugging in x equals 6 or -6 in here. So I'll just divide up my page a little bit here. Boop, boop, boop. If I plug in -6, -6 plus 2 is still a negative. -6 plus 3 is still a negative. So a negative times a negative gives me a positive. Right? That's all I'm looking for. A positive, I want it to be greater than 0. So this is a solution. Since x plus 2 times x plus 3 is greater than 0, which is positive in this region. Well, if I plug in -2.5 plus 2, right? No, I guess I'll write it out. X plus 2 times x plus 3, plugging in -2.5, -2.5 plus 2 is going to be a negative. -2.5 plus 3 makes a positive, so here I get a negative value, which is not a solution. Since we need it to be greater than 0. Same thing here, x plus 2 times x minus 3. If I have 0, I get a positive value. 0 minus 3 makes a negative value, so a positive times a negative makes a negative value over, hey, 0 plus 2, oh, because I wrote it out wrong. X plus 3. Bing, bing. It is. Thanks, Kayla. Yeah, going too fast. So this is a solution. Okay. So therefore, right, our solution is anything up to -3, but not including -3, because then it would be equal to 0, which is what we don't want, right? So our solution here is from -infinity up to -3, but not including -3. As well as from -2 up to positive infinity, right? But also not including -2, because so remember we use that u or, so from -infinity up to -3, not including -3, or from -2 up to positive infinity is our solution. Graphically, or on a number line, it'll look like this. So we've got -3, -2. Oops, not like that. Open dot, open dot. Or, right, if we need it to be positive, so if we're saying, okay, over here up until -3, it's positive, positive, and then at -3 to -2, it gives us negative results, and then at -2, we get positive results. So what this thing looks like is -3, -2. Here we've got positive values, dipping down for negative values, and then it goes back up. Okay. I was gonna do 51, but what I actually want to do is I want to talk about those absolute value inequalities. So I think what we'll do is we'll use 51 as a quick review next day. So work on it kind of on your own, right? So 51 is this one here. I want you to try it on your own, and then we'll use it to do an actual review of this stuff next day, because that'll be good. So I'll make a note, use for review next day. Note to myself. Because I want to get into these absolute value inequalities. And then we can deal with lines next day. Maybe I'll do this whole, I'll do a cutout of everything. Ha. Okay. So absolute values, remember, use those vertical lines around some value. And if the value inside is negative, we essentially just drop the negative, right? Or technically we take the negative of that negative number and it gives us a positive. Now, when we have inequalities dealing with absolute values, they behave a little bit differently. And so we need to really kind of stop and think about how these things behave. If the absolute value is on the lesser side of the inequality, then we're safe. So what we do is we can just rewrite this as x is between negative c and c if the absolute value of x is less than c. Same thing if it's less than or equal to, right? We just change the sign or the inequality in here to include those endpoints. The hard part is if the absolute value of x is greater than some value or greater than or equal to some value, okay? Then we've got these kind of two situations where it looks like this, right? It can be this or this. Right? So to solve these inequalities, right, we just need to keep these rules in mind, and then we're gonna rewrite these, and then we're essentially back to where we started, where we're just solving these inequalities, right? Once we've gotten rid of those absolute values, then we're just back to inequalities with values on either side. So let's do, let's do something like x minus 5. Let's start with 79. The absolute value of x minus 5 is less than or equal to 3. Okay. Because we're just starting with inequalities, let's refer back to this little chart here. So we've got an absolute value less than or equal to some number. So how I can rewrite that is, so this, we can rewrite this as x minus 5 goes in the middle, and it's between negative 3 and 3 to solve for x. Okay. So now it's actually pretty simple because we've gotten rid of that absolute value sign by putting it between negative 3 and 3. And so now all I have to do is add 5 to both sides, and then I'll have solved for x, right? And so now I have negative 3 plus 5, right? Adding 5 to both sides of the inequality, or all sides, I should say, which is back to where we started. X has to be less than or equal to 3 plus 5. Oops, I'll do that in a different color just to show where it went. Notice that I'm not showing the x minus 5 plus 5. I'm just writing it as x, and that's what we'll start to move towards. So what I get, negative 3 plus 5 is 2. It has to be less than or equal to x, which has to be less than or equal to 3 plus 5, which is 8. And just like we were doing before, you can check your work, but here I'm feeling pretty confident, and I want to get to kind of a harder one. So that is it. So the solution looks like including 2 up to 8 inclusive in interval notation. We can graph it too, but so let's do one that's a little bit harder, right? When we've got the greater than sign, that's when it becomes a little bit harder. So I'm gonna look for something with a greater than, let's do 84. Why not? The absolute value of 8x plus 3 has to be greater than 12. So if we go back and look at our rules, how we can rewrite this without the absolute value is that x has to be less than negative c. Negative c in this case is negative 12, or 12 has to be less than x, right? So here, I'm just going to steal this, copy, so I can use it down here, right? Because I've got 8x plus 3 is my x, and 12 is my c, and so the solution here is going to be 8x plus 3. Notice that I've gotten rid of that absolute value. That's the whole goal. 8x plus 3 has to be less than negative 12, or 12 has to be less than 8x plus 3. Now I'm solving each of these for x. Solve each of these for x. So now, if I'm solving for x on this side, right, let's put it on a fresh page here. 8x plus 3 has to be less than negative 12. So 8x plus 3 has to be less than negative 12. I have to move that 3 over, so I get 8x is less than negative 12 minus 3. Because I'm just subtracting, I'm safe, right? Negative 12 minus 3 is negative 15, so x has to be less than negative 15 divided by 8, which is simplified, so I'm just going to leave it like that. Or 12 has to be less than 8x plus 3. Same thing, 12 minus 3 has to be less than 8x. 12 minus 3 is 9. Has to be less than 8x. So 9 divided by 8 must be less than x, which I can't simplify. So now my solution here is, okay, x has to be less than negative 15 over 8, but x has to be greater than 9 over 8. Okay? So it has to be greater than 9 over 8 and less than negative 15 over 8. So what I'm going to do is I'm going to rewrite this as an interval notation and this in the interval notation. I'm not going to smush them together, but we have to go kind of across the number line. So here, this is the same as saying x has to be less than negative 15 over 8. So from negative infinity to negative 15 over 8. And then here, if x has to be greater than 9 over 8, you're going from 9 over 8 up to infinity. So the overall solution is where we join these. So, oops, or, but keep the same color. So the solution is going to be negative infinity to negative 15 over 8. U for union, right, which means or. Up to 9 over 8 up to infinity, not inclusive on either side. Just like that. Okay. So try those other questions that are in the notes, just for practice, right? Just to see what we're doing here. Are there any questions? So we'll keep going through. So try number 51 from earlier on your own, and then we'll start with that one next day. And then we'll keep going with lines, which I think you'll find a lot easier than this stuff. This stuff is hard, right? Inequalities are tricky. But we did it. I'll hang tight for questions, but I'll stop this recording.